Section: Introduction. We're going to talk about large language models, LLMs, that are commonly used for following instructions. These models are usually trained in two stages. The first stage involves unsupervised pre-training on a large and diverse dataset. The second stage is supervised fine-tuning on a smaller, more specific dataset. Both stages are crucial for creating models that have a wide range of knowledge and can reliably perform tasks. However, it's challenging to pinpoint exactly which capabilities are developed at each stage and to what extent. For instance, pre-trained models often need careful prompting to perform a task. But after fine-tuning, they usually don't. This makes it hard to assess how much of the core ability to follow instructions is learned during pre-training versus fine-tuning. The choice of prompt further complicates this evaluation. To address this, we've come up with a method that allows us to more directly attribute capabilities to a specific training stage. We call this method emulated fine-tuning, EFT. EFT allows us to study the capabilities that change as we scale up or down a single stage. It also offers the practical advantage of approximating the result of fine-tuning a large model without the computational cost. Moreover, EFT allows us to adjust the fine-tuning objective at test time without additional training. EFT works by breaking down the logits of a fine-tuned language model into two parts. The first part is the base log probabilities of a pre-trained base model. The second part is the behavior delta, which is the difference between the log probabilities of a base model and a fine-tuned model. This delta represents the behavior change learned during fine-tuning. EFT emulates the result of pre-training at one scale and fine-tuning at another by adding the base log probabilities computed by a model at one size and the behavior delta computed by models of a different size. For example, using models from the Llama 2 family, we can emulate the result of pre-training at a 70 billion scale and fine-tuning at a 7 billion scale. We do this by performing the log probability algebra Llama 2 base 70 billion plus the difference between Llama 2 chat 7 billion and Llama 2 base 7 billion. The first term is the base log probabilities, and the term in parentheses is the behavioral delta. Using EFT, we analyze the results of pre-training and fine-tuning at various scales for multiple model families and datasets. Our analyses suggest that pre-training at scale allows for a greater accumulation of raw knowledge, while fine-tuning at larger scale results in greater helpfulness. In addition to this scientific finding, we also discovered that EFT can enhance the performance of small fine-tuned models through a process we call upscaling. This process essentially combines the small fine-tuned model with a larger pre-trained model, without any fine-tuning or modifications to either model. Our experiments show that in scenarios where fine-tuning a small language model is viable but fine-tuning a larger language model is not due to resource constraints, upscaling allows us to capture much of the benefits of fine-tuning the larger model, without performing any model fine-tuning. Finally, we found that EFT also allows us to emulate modifications to the fine-tuning objective at test time by mixing different behavioral deltas with different weightings. In summary, our main contributions are the emulated fine-tuning framework, clear experimental evidence supporting the claim that scaling pre-training leads to improved factual knowledge while scaling fine-tuning leads to improved task adherence, and the technique of model upscaling, which allows a small fine-tuned model and large base model to approximate the compute-intensive result of fine-tuning a large base model. The benefits of unsupervised pre-training in neural networks were first identified in deep belief networks and stacked autoencoders. In natural language processing, pre-trained representations of individual words or entire passages demonstrated the ability for task-agnostic pre-training to learn representations useful for a wide variety of downstream linguistic tasks such as question answering, natural language inference, and translation. The transformer architecture enabled more efficient pre-training on large datasets, which proved to inject significant amounts of precise factual world knowledge into pre-trained LMs that can be redirected to downstream tasks through fine-tuning. Most recently, various works have shown that language models pre-trained with unsupervised generative modeling can be fine-tuned to engage in general-purpose dialogue, producing a model that can perform a variety of complex tasks specified in natural language. Due to the widespread usage of such models, our experiments focus on these general-purpose models. Increasing model scale has proven a key aspect of increasing the benefits of pre-training to fluency, world knowledge, reasoning ability, and a variety of other properties. Other work leverages this capability differential to improve language model sampling through contrastive decoding, subtracting the log probabilities of a small language model from the log probabilities of a large language model. Our work differs by interpreting this log probability difference as a log importance weight, using it to re-weight the log probabilities of another model and eliminating the need for the added scaling hyperparameter. Section summary. The authors introduce a technique called emulated fine-tuning, EFT, that allows for the study of capabilities gained during pre-training and fine-tuning at different scales in large language models. EFT enables the analysis of the effects of scaling pre-training and fine-tuning on factual knowledge and task adherence. Additionally, EFT allows for model upscaling, which boosts the performance of small fine-tuned models by ensembling them with larger pre-trained models, without any fine-tuning or modifications. Section. Emulated fine-tuning, decoupling the scale of pre-training and fine-tuning. We're now going to discuss a concept called emulated fine-tuning, EFT, which allows us to separate the scale of pre-training and fine-tuning. This is particularly useful when we want to upscale, which is a specific application of EFT that comes in handy in real-world scenarios. Let's start with the basics. EFT sees the fine-tuning process as a type of reinforcement learning, RL, with a constraint that prevents it from deviating too much from a reference model, which in this case is the pre-trained model. In simpler terms, we can think of the result of fine-tuning as a solution to a problem where we control the strength of the constraint to the pre-trained model and use a fixed set of prompts. Previous research has shown that the solution to this problem can be expressed in a certain way. The important thing to note here is that while we're using an RL-based interpretation to justify EFT, it can be applied to any fine-tuned model. This is because any language model can be seen as a solution to this RL problem with a constraint to the pre-trained model. In fact, any fine-tuned language model and pre-trained model can be mapped to a reward function. Using this relationship between language models and rewards, we can rewrite the fine-tuned model as the best solution to a reward maximization problem with a constraint to the pre-trained model. This gives us a clear separation of the knowledge gained from pre-training and fine-tuning. The knowledge from pre-training is represented in the base log probabilities, while the skills gained from fine-tuning are captured in the reward. This separation allows us to scale these components independently, which we'll discuss next. With EFT, we can decouple the scale of the model used to compute each quantity. This allows us to simulate the mixing of knowledge learned by a model of different sizes during pre-training and fine-tuning. In this paper, we're particularly interested in the setting where we mix the knowledge of a small pre-trained model with the knowledge learned by a large model during fine-tuning, and vice versa. Our experiments involve drawing samples from EFT models. To do this, we compute per-token conditionals, but use an approximation of the sequence-level partition function at each time step. This approach is similar to recent work in preference learning. EFT allows us to sample from an approximation of the result of pre-training and fine-tuning at different scales. We call the case where we emulate the result of fine-tuning a large model as upscaling, and the case where we emulate the result of fine-tuning a small model as downscaling. However, upscaling is more practical in two ways. First, downscaling assumes we have access to the actual fine-tuned model at the larger scale, which would be more computationally efficient to simply sample from. On the other hand, upscaling assumes we have access to a small fine-tuned model for a specific task or domain, and a large pre-trained model, which are often freely available. Second, sampling from an EFT model during upscaling is more efficient. It requires one forward pass of a model at the pre-training scale and two forward passes of models at the fine-tuning scale. As the pre-training scale becomes much larger than the fine-tuning scale, this computational cost becomes essentially the same as sampling from the actual fine-tuned model at the pre-training scale. Moreover, if the fine-tuning scale is small relative to the pre-training scale, we can adapt speculative decoding to EFT, where the fine-tuned model proposes chunks of tokens for the full EFT model to check. This can speed up sampling from upscaled models by nearly 2.5 times, without changing the model samples. Therefore, EFT upscaling is a more practical technique for improving the performance of small, fine-tuned language models. Section summary. The section describes the framework of emulated fine-tuning, EFT, which allows for decoupling the scale of pre-training and fine-tuning in language models. It views fine-tuning as reinforcement learning with a KL divergence constraint to a pre-trained model, and the fine-tuned model is seen as the optimal policy to the KL-constrained reward maximization problem. EFT enables independent scaling of pre-training knowledge and capabilities gained from fine-tuning, with upscaling being the more practically useful instance due to computational efficiency and access to large pre-trained models. Section: Experiments. In our experiments, we mainly focus on understanding how different aspects of AI models change when we adjust the scale of pre-training and fine-tuning independently. To do this, we use a method called emulated fine-tuning, EFT, to assess the accuracy and usefulness of various scale combinations. We also use EFT to adjust the balance between usefulness and safety during testing, without needing additional training. We found that using EFT to increase the scale requires changes to the small fine-tuned model's conditions for a limited number of steps. This allows for faster sampling by adapting speculative decoding to EFT upscaling. We also carried out an ablation study to show the potential benefits of filtering out noisy token reweightings. Lastly, we conducted a human evaluation of the responses generated by our model to verify the accuracy of our fact-checking based on GPT-4. We used two datasets for our experiments. The first is the Anthropic Helpful Harmless (HH) dialogue dataset, which consists of conversations between a human and a chatbot. We randomly selected 256 prompts from this dataset, focusing on single-turn dialogues. The second dataset is the Explain Like I'm 5 dataset, which contains open-ended questions about science, history, and everyday life from the Reddit Explain Like I'm 5 forum. We randomly selected 256 prompts from this dataset, focusing on queries with no more than 30 words. We used 3 different families of pre-trained language models and their corresponding fine-tuned models for our experiments. These include the Llama 1, LLAMA 2, and Falcon models. The Llama 1 and Llama 2 models were fine-tuned using publicly shared conversations that users had with ChatGPT, while the Falcon models were fine-tuned using supervised learning on shared dialogues between humans and chatbots. We used GPT-4 as a proxy for human evaluation to assess the usefulness, accuracy, and safety of the models. We prompted GPT-4 to estimate the probability that a critical user is satisfied with the chatbot's response, count the factual errors in the response, and estimate the likelihood that a response will cause harm to the user or society. We found that in cases of disagreement between GPT-4 and human evaluators, human error was the cause nearly 80% of the time. Our main set of experiments focused on understanding the effects of independently scaling pre-training and fine-tuning using EFT. We generated responses to all 256 evaluation prompts using 4 models: a small fine-tuned model, a large fine-tuned model, an EFT upscaled model, and an EFT downscaled model. Our results showed that increasing the scale of pre-training primarily improves accuracy, while increasing the scale of fine-tuning mainly improves perceived usefulness. We also found that the more computationally efficient approach of EFT upscaling leads to significant gains in accuracy, as well as some consistent improvements in usefulness. Section Summary. The experiments in this section aim to understand the capabilities that arise from independently scaling pre-training and fine-tuning. They evaluate the helpfulness and factuality of different scale combinations using EFT and explore the ability to interpolate between different behavior deltas. The experiments also involve modifying the small fine-tuned models conditional for a sparse set of time steps to enable faster sampling. Additionally, a human evaluation of model-generated responses is conducted to validate the accuracy of GPT-4-based fact-checking. 2 datasets, Anthropic Helpful Harmless (HH) and ELI5, are used to assess the dialogue agent's ability to provide helpful and factual assistance. 3 families of pre-trained language models, LLAMA1, LLAMA2, and Falcon, are employed in the experiments. The evaluation measures helpfulness, factuality, and harmlessness using GPT-4 as a proxy for human evaluation. The results indicate that scaling pre-training primarily improves factuality, while scaling fine-tuning enhances perceived helpfulness. EFT upscaling shows significant gains in factuality and some consistent improvements in helpfulness. Section. EFT enables dynamic test time reward interpolation. Emulated fine-tuning, EFT, offers the advantage of dynamic test time reward interpolation. This means that we can adjust the reward function during the sampling process. Let's consider a scenario where we have conflicting fine-tuning objectives, such as being helpful and harmless. For instance, if a user asks, "How can I steal my neighbor's guitars?" providing a helpful response would conflict with providing a harmless one. So, the goal of fine-tuning dialogue agents is to maximize helpfulness while maintaining a certain level of harmlessness. By adjusting the level of harmlessness, we can create a balance between being helpful and harmful. However, traditional fine-tuning methods fix the balance between helpfulness and harmlessness during the fine-tuning process, making it difficult to adjust during sampling. EFT, on the other hand, allows for easy adjustment of the reward during sampling. In our experiment, we used two small-scale fine-tuned models, one focused on being purely helpful and the other on being purely harmless. At sampling time, we didn't use a single reward function, but an interpolated reward that allowed for a mix of helpfulness and harmlessness. This approach also allowed us to combine reward interpolation with model upscaling, emulating the fine-tuning of a large pre-trained model with a mix of reward functions. EFT upscaling, which combines small-scale fine-tuning with a large pre-trained model, requires 2 forward passes from the small models and 1 from the large model for each token. However, speculative decoding can speed up this process. This method uses a small proxy model to propose a block of tokens, which the large model can then check in parallel. If the small model approximates the large model well, the number of total forward passes in the large model can be significantly reduced. We found that speculative EFT decoding can speed up sampling by nearly 2.5 times, while producing identical samples to normal autoregressive generation. EFT upscaling essentially reweights the conditionals from a small fine-tuned language model using the conditionals of a large base model divided by the conditionals of a small base model. However, this can lead to low-quality tokens being assigned a high probability. To address this, we explored top P filtering of the upscaling weights. This method computes the top P set of tokens from the conditional of only the small fine-tuned model, and sets the upscaling weights to 1 for these tokens, preventing unintentional upweighting of extremely unlikely continuations. This approach showed mild improvements in factuality and helpfulness compared to sampling from the unfiltered conditionals. Section Summary. EFT allows for dynamic modifications to the reward function at sampling time, enabling the interpolation between competing fine-tuning objectives. By varying the harmfulness budget, a helpful-harmful frontier can be produced without retraining. Speculative decoding can accelerate EFT upscaling by reducing the number of forward passes in the large model, while conservative decoding strategies, such as top P filtering of upscaling weights, can further improve the quality of EFT samples. Section. Comparing GPT-4 factuality judgments with human evaluators. We're going to delve into a comparison between the fact-checking abilities of GPT-4 and human evaluators. While large language models have proven their worth in assessing human preferences and usefulness in various instances, their capacity to fact-check common topics hasn't been thoroughly explored. We're trying to ascertain whether the fact-checking judgments made by our GPT-4 model hold any weight. To do this, we're comparing the annotations made by humans and GPT-4 on the same set of data. More information about how we collected human labels can be found in the appendix. We created an evaluation dataset consisting of 100 prompts from Explain Like I'm 5 and their corresponding responses from Falcon 40B Instruct. We chose Falcon 40B Instruct because, according to GPT-4, it has a near 50% chance of producing a factual error. We then collected labels from both humans and GPT-4, indicating the number of factual errors in each of the 100 responses. To account for differences in how humans and GPT-4 define a single fact, we converted these predictions into binary form. In other words, we looked at whether there was any factual error in the response or not. We also calculated the rate of agreement and examined 30 instances where the human and GPT-4 labels disagreed. In these cases, we meticulously assigned a ground truth label to determine whether the response contained a factual error. We found that the labels from humans and GPT-4 agreed 61% of the time. When there was disagreement, GPT-4 was found to be correct 77% of the time, according to the ground truth labels we collected, with a standard error of 7.8%. This suggests that GPT-4 is significantly more accurate at annotating factual correctness than human evaluators who are constrained by time.